Hi everyone, I'm Hang Zhao. I'm very honored to be here to share our recent works on autonomous driving. I'm also very glad to see all the old friends in this workshop. The title of my talk today is Vision-centric Autonomous Driving from Perception to Prediction. In the past 2 years, our group have been very actively working on the topic Vision-centric Autonomous Driving, or VCAD. We have published or released a series of papers on this topic, including Data 3D for 3D detection, Filter 3D for sensor fusion, Muter 3D for multi-object tracking, VIP 3D for trajectory prediction, HDMapNet and VectorMapNet for mapping. If you are interested, feel free to check out our project website for more details. The first question that may come up is, why do we care about vision-centric autonomous driving? As we know, in the past decade, self-driving solutions are heavily reliant on LiDARs and HD maps. Vision, in comparison, is underexplored. However, vision contains rich attributes beyond geometry, and it helps us with holistic scene understanding. The second reason that we care about vision-centric autonomous driving is scalability. Compared to LiDARs, vision is more affordable for all vehicles. What is more important, vision has mature protocols for data collection, data compression, data transmission, and etc. We can expect more visual data being used in machine learning than any other sensors. Finally, vision-centric does not mean vision only. I believe that multimodal learning is the key for the safety of self-driving cars. So we should work on vision-centric sensor fusion technologies as well. Our papers on VCAD can be categorized into two groups. Given surround view images as input, as shown on the left, the first group of papers aim to understand the static map environments around the vehicle. And the second group aim at understanding the dynamic agents around the vehicle. So we are now able to understand both the static things and dynamic things. In today's talk, I will pick two most recent papers, one from each group. The first paper I would like to share is called VectorMapNet End-to-End Vectorized High-Definition Map Learning. Here's the background. Classical methods of annotating and maintaining high-definition maps involves a very complicated pipeline, as shown in this figure. Normally, we have a fleet of survey vehicles equipped with LiDAR scanners, IMUs, GPS, wheel odometry, drive around the city to collect a bunch of point cloud data. Then we will perform point cloud registration to get a globally consistent point cloud map. After that, we will recruit some map experts to annotate on the point cloud maps to find out all the semantic elements in the map so that we have a globally consistent semantic map. After obtaining the global semantic map is not enough. For a self-driving car, it has also need to perform a centimeter accurate localization so that it knows what the environment around it. This whole process is very complicated and complex, and it is costly and labor intensive. Moreover, road conditions are ever changing. To enable long-term use, high-definition maps demand constant updates and maintenance. So, we propose to make online inference of local maps with neural networks. It takes as input camera images or LiDAR point clouds, or both of them, and directly outputs a local vectorized semantic map. This will be a very simple pipeline, and it is cheap and automatic. It also perceives dynamic environment directly, turning a mapping problem into a perception problem. So we no longer need to wait to worry about map updates anymore. Recent works, including Lift Splash Shoot and our paper, HDMapNet, formulate this problem as a rasterized map segmentation problem. Here's the idea. They first convert the perspective view images into a bird's eye view space, and then performs pixel-wise labeling in the bird's eye view space, such as lane markings, pedestrian crossings, and etc. This is nice, right? We can get a bird's eye view semantic map. However, we find that it is hard to enforce spatial coherence in the predicted segmentation map. For example, the two pixels that are nearby can have very different semantics, predicted semantics. What is worse, the semantic maps are incompatible with most downstream modules, which usually takes vectorized inputs. So most often, the post-processing operations is required. So meaning that it's not fully end-to-end. That is why we want to propose a new end-to-end model called VectorMapNet to directly output the vector maps. Here's the solution. First, we use polyline as a unified primitive to represent map elements. For example, the curves, like the lanes, can be sampled into polylines. Polygons, for example, a parking area or pedestrian crossing, those polygons can be represented as closed-form polylines. Points such as traffic light, traffic signs, they can be represented as polylines with only one node. Therefore, we have a unified representation, that is the polyline, to represent all the map elements. This is nice, right? Then we pose this problem as a detection problem and hope that map detection is not very much different from object detection. As we know, object detection is from an image we want to detect a bunch of bounding boxes. Now for map detection, we basically, from the images as input, we want to detect a bunch of polylines. Now these two problems are more similar. And finally, we design a detection transformer-like model to solve this vector map detection problem. Because this model architecture design can avoid non-differentiable operations such as NMS. Here are more details. As shown in this picture, on the left is the input onboard sensor data, and on the very right is the output vectorized map. Our model first projects the sensor data into bird's eye view space by a BEV feature extractor. Then, a second module called Map Element Detector detects map elements' locations and categories based on the learnable queries and BEV features. Finally, a module called a polyline generator decodes the elements into polylines of different lengths. And that works for every map element. So composing everything together, we get a vectorized map as the output. Here are some qualitative results. On the left, we show ground truth map, and on the right, we show the predictions of VectorMapNet. The dark green lines, polylines, are the road boundaries. The yellow polylines are the lane dividers. And we also have gray polylines, which are the center lines of the lanes. These center lines of the lanes are not visible, but they are very important for the self-driving cars to follow. And we have another set of visualizations. Our model also detects pedestrian crossings. Okay, the results look very good. Then the next question is whether it is useful, right? So we show that the predicted maps are actually compatible with downstream tasks like motion prediction. We observe motion prediction performance improvement when using our predicted map, as shown in the last row. The first row is a motion prediction model without map input. The last row is our predicted map, and the second row is the ground truth map. And we can see that the performance gap of our map compared to using ground truth map is not very large. Cool, that's about mapping. And the next paper I'm going to talk about is VIP3D, end-to-end visual trajectory prediction via 3D agent queries. As the name goes, we predict future trajectories of agents from visual inputs. Why do we want to work on visual trajectory prediction problem? Traditional perception and prediction pipeline separates detection, tracking, and prediction modules, and their interfaces are manually defined. For example, 3D bounding boxes, trajectories, and maybe some other attributes as well. In VIP3D, we want to take advantage of the rich visual information from the input images for the motion prediction module. They're very far away in the pipeline, and we want to propagate all these information. And here are some intuitive examples to show that why do we want to do this. For example, in this picture, we show a vehicle with a turning signal that is on. And these signals, it can be implicitly encoded by a neural network, propagate for prediction, and finally, our model can understand that the vehicle intends to turn. And we have better examples for pedestrians. We know that a person's pose and gaze show his or her intentions. And these informations are lost in the traditional pipelines because the interface are only boxes and the trajectories. And we hope a deep neural network can capture all these details. Second, why our model is an end-to-end model. An end-to-end model also enjoys other benefits. For example, it can avoid error accumulation in the pipeline, and it prevents from data distribution shift as well. Now let's take a look at the model architecture of VIP3D. At each time step, we have multi-view images as input, as shown on the top. We use a set of 3D agent queries to aggregate visual features through 3D to 2D cross-attention in order to detect agents. More concretely, the model architecture we use here for detection is Deter3D. The input to the Deter3D model is a bunch of 3D agent queries. We send them into a transformer decoder to decode them into 3D boxes. Those 3D bounding boxes have physical coordinates. So we make 3D to 2D projections onto image feature maps with the camera intrinsic and extrinsic parameters. This process is deterministic because this is from 3D to 2D. Then we sample the features from these corresponding image feature maps and concatenate them with the positional encodings of the 3D bounding boxes. Then the concatenated features will be sent back to a transformer decoder to further refine the box predictions. This process is iterated for several times. After object detection, the queries further interact with high-definition maps and are decoded into predicted trajectories. More concretely, here we use VectorNet, a model VectorNet, to make trajectory predictions. Each map element is encoded and becomes a node in a graph neural network. The agent queries interact with these nodes in the graph neural network through attention and are further decoded into multiple future trajectories. Okay, then we move to the next time step, t equals to 1. The agent queries are managed in a dynamic memory bank. We only keep the queries that have detected an object at t equals to 0, the orange one. And we threw away the two other queries that are empty. Then at t equals to 1, we'll complement two new empty queries in case there are new objects appearing in the new frame. So again, we have 3 agent queries. They will further extract visual features and predict corresponding trajectories. Then comes the next frame, t equals to 2. The model works very similarly, tracking old objects, detecting new objects, and predicting their corresponding trajectories. It is worth mentioning that the VIP3D model works in a concise streaming manner, with these 3D agent queries initialized, updated, discarded over time. And quantitatively, VIP3D outperforms traditional pipelines and a CNN-based model called PNPNet. We have also performed a bunch of ablation studies on VIP3D, and we have 2 interesting and important findings. First, the differentiability is very important for the final performance. And second, we know that in traditional trajectory prediction problems, historical trajectories are used as the input of the model. But now for VIP3D, the inputs are only agent queries. And we also try to complement it with historical trajectories, and we find that there's no performance improvement. This shows that the agent queries has captured all this rich information, including the trajectories, together with other visual textual information. And in the visualizations, we have also found some interesting cases. In this example, a pedestrian in this blue box is turning his head and looking at our self-driving car. So he should be waiting for us. However, we found that the traditional methods cannot capture such fine-grained information and makes a wrong prediction of crossing the road, shown in the red trajectory. Our model VIP3D makes it correct. The prediction is in orange. Finally, here is a video demo of VIP3D. The images at the top are the input camera images, and at the bottom we show the animation shows the outputs of VIP3D. Hope you can watch it smoothly through internet. The results are by no means perfect, but I believe that with more efforts putting into vision-centric autonomous driving, we can make it much better. Okay, at the end, I would like to acknowledge all the contributors. First, my students, Yichen Liu and Junru Gu. They are the first authors of these two papers, and they did most of the work. And also my collaborators, Yue Wang, Yilun Wang, Chenxu Hu, Tianyuan Zhang, Xuanyao Chen from many different institutes. They also contribute a lot to these projects. Okay, that's everything I have for today. And if you have questions, feel free to raise any. Thank you.